All right, so this video is going to look at calculating pHs of acids. We're going to focus first on strong acids. We've actually already calculated pHs of strong acids for the concentrated solutions because strong acids are going to completely dissociate into their respective ions, hydrogen ions and the conjugate base of that acid. And so their concentration of hydrogen is the same as the concentration of their parent acid, and the hydroxide would just be 10 to the negative 14th over that hydrogen concentration. Super duper small. If you happen to have a strong acid solution that is very dilute, that ends up having a greater concentration of hydrogen ions due to water than due to the acid, water is going to determine its pH, and it would just be 10 to the negative 14th of that hydrogen concentration. 50% of the kW of water would be your hydrogen ions. Half of water is hydrogen, half of water is hydroxide. So you would have in a dilute solution, because it would be neutral, equal amounts of the hydrogen and hydroxide ions. So we're going to look at a concentrated strong acid solution, the 0.250 molar HNO3, as well as a diluted solution, 2.50 times 10 to the negative 10th molar. So the biggest thing I can tell you with your strong acids, once you've identified it's a strong acid, take a look at the value of the concentration. If it is smaller than 10 to the negative 7th, the pH of your solution will be the same no matter what, because acidic solutions cannot be basic. So strong acid, my species presence would be the hydrogen and the nitrate ions. The concentration of hydrogen is the same as the acid, 0.250 molar. The pH would just be the negative log of that and give me a value of 0.602. With my 2.50 times 10 to the negative 10th molar solution, water is going to be my dominant species. So my hydrogen concentration will be half of water. Water's kW, 1 times 10 to the negative 7th. And if I take the pH of that value, I'm going to get that that solution is neutral. So you cannot, again, have a pH greater than 7 for an acidic solution, but if you have a very, very dilute strong acid, water is going to determine the pH, which will make it be neutral. When it comes to using pH to find the concentration, because there's only going to be one proton dissociated from each of the strong acids when they're in that strong form. We only have one diprotic acid, H2SO4, and even with H2SO4, only one proton comes off. We can use the pH to find our hydrogen concentration, and then use our hydrogen concentration to directly find the concentration of our acid. There's no stoichiometry involved like with the bases, because you only have that one proton. So our solution consists of hydrogen and nitrate ions. You do not have to write these major species out. This is just to kind of help you understand why it is we're not doing equilibrium problems with these, because they completely dissociate. We have none of that original acid in its intact form. So if I use my pH to find my hydrogen concentration, I get that that would give me a value of 7.9 times 10 to the negative 6th molar, which would be the same as the nitric acid, because hydrogen ions are going to have the same concentration as their parent acid when you're dealing with a strong acid. With weak acids, things are a little bit different because, again, the majority of the acid stays intact. Only a small fraction is formed from the hydrogen ions, or from the parent acid to form hydrogen ions and the conjugate base. So the hydrogen source is going to be the acid, but because of the weak dissociation taking place, we have to use our equilibrium constant to determine what fraction of hydrogen ions are produced from that weak acid. Once we have those hydrogen ions, we can use that and kW to find the hydroxide. Typically, the smaller your hydrogen concentration, the larger your hydroxide concentration will be, and vice versa. So when you're setting up these pH problems involving weak acids, you want to write an equilibrium expression for the dominant equilibrium, which 99% of the time is going to be the acid. You hopefully are going to get to a point where you're not going to need to set up these ice charts so much, but for right now, you're probably going to want to. We are going to exclude the X because these are only going to weakly dissociate. So in terms of the change in the initial acid's concentration, we're going to assume that it is not changing enough for us to consider it in our calculations. And once we have what that value of X is and we know what our hydrogen concentration is, we can use that to calculate what we're looking for. Again, we talked about that 5% rule when I first talked about ignoring the X in equilibrium problems where the K is very small. This is what percent dissociation is, basically the amount that breaks off, the amount that dissociates your X over the initial concentration of your acid times 100. And again, as long as that's smaller than 5%, we're totally good with disregarding the X. And I'll be honest, that's all you're going to run into for the most part, unless you're given a percent dissociation problem, then you would have to use it. So for this weak acid, it says the percent dissociation value will increase as the acid becomes more dilute, because even though the amount dissociated is going to diminish, the initial concentration is going to diminish much more. And so that's going to help to increase that parent percent dissociation value. So here we have an acid, C6H5CO2H. I believe this is benzoic acid, and we're given its concentration 0.250 molar. So when we take this acid and we place it in water, it's going to produce hydrogen ions in the form of H3O plus as the acid donates its proton. Water's going to accept it, and then what's left is the conjugate base of that parent acid, C6H5CO2 minus. My Ka expression would include all but the water. So I have my two products over my one reactant. And that is equal to, according to my table, 6.3 times 10 to the negative fifth. Again, I'm setting this up for you initially, but my hope is you're going to reach a point where you're not going to need to do these ice charts so much for these just straight weak acid or weak base problems. We have initial concentration of 0.250 molar. We do not have any of our products, which means that Q is less than K. We're going to need to take away from our reactants and add on to our products. Again, because if we look at this K, 6.3 times 10 to the negative fifth, and we look at the concentration of our acid, 0.250, there's a pretty substantial difference between the two. So with that in mind, we're going to disregard that X and just solve for what X would be if there is no change in our initial reactant's concentration. And when you do that, you don't have to use all that graphing stuff that we've been doing in class. I get an X of 0.004. That X is my hydrogen concentration, so that's telling me what fraction of hydrogen ions are present in my mixture, and I can use that to calculate pH. To verify that my assumption about ignoring the X was reasonable, I take the percent it dissociated, and the amount it changed by, and I divide it by the initial concentration, and that's how I'm going to calculate the percent dissociated. And I want a percent dissociation less than 5%. It was 1.6, so this was a very reasonable assumption for us to make. If you had taken X away from 0.250, you would have gotten 0.246. Again, not drastically changing the concentration of that original acid. But I now know my hydrogen concentration, so I can take the negative log of my value of X, and I get that my pH would be 2.40. Here we're going to do this with another acid, HCN. Again, it's a weak acid, so primarily it's going to stay intact along with water being present. I write my dissociation equation where I have my acid donate its proton to water acting as a base, producing hydronium ions and cyanide ions. I can write my K expression excluding water, and from my chart I get that that's equal to 4 times 10 to the negative 10th. So this K is even smaller than the one we just did. Definitely going to be a logical assumption to disregard the X. Same as before, I had my initial quantity of HCN. I had none of my products. So seesaw, reactants go down, products go up. When I substitute into my expression, we're going to disregard the X with HCN. And when we solve for X, we get a value of 1 times 10 to the negative fifth. That is really, really small. It is definitely not going to change the concentration of that initial acid. If I do my 5% rule, it's going to be even smaller than the 1.6 we saw in the previous slide, 0.004%, well within that 5% range. But I now know what X is, which is my hydrogen concentration, and I can use that to calculate pH. 5.00. So I think this is the last one with our acids. We have a 0.1 molar solution of HF, and the percent dissociation is 8.1%. So that's higher than 5%. So that's going to play a role in our calculations. We want to use this information to calculate Ka. So we're doing things a little bit differently than we've done before. We still have a weak acid, and if we still place it in water, we're going to produce hydrogen ions and fluoride ions. We have our equilibrium expression, so we want to find what the equilibrium concentrations are of our two products and the one reactant that we include. Percent dissociation gives me what that change is, so that's going to help me find the hydronium concentration and the fluoride concentration when I compare it to my initial concentration of acid, 0.100 molar. Multiply that by 100 and that all equals 8.1%. So if I go through and solve for X, I get that it is 0.0081 molar. I now know what the concentration is of my hydrogen ions and my fluoride ions because they would both increase by X. If we go back and look at one of the previous two problems, we didn't have any products. X is what we made of our products. Because our percent dissociation was greater than 5%, we don't get to disregard the X on the reactant side this time, which is why you see 0.1 minus X, 0.0081. And I go through and do my calculation, and I get that my Ka is 7.1 times 10 to the negative fourth. And I'm pretty sure if you take a look at your notes, or that table I gave you in class, you're going to see that's pretty close to the Ka value for HF.